Bismillah ar-Rahman ar-Rahim. We are going to start discussing sound waves. Remember that in the previous videos we discussed waves in a string, and those type of waves are called transverse waves. Now we are going to move to longitudinal waves, where the waves, the best example is sound waves. So we are going to look at sound waves in different media, let's say in air, in water, and of course a wave, as we said, a mechanical wave requires a medium, and the medium will be the air, or will be water, or will be a solid like steel, and so on. So to produce a wave, we need the medium, and we need the disturbance, of course. So sound waves are they are longitudinal waves, by the way. So we call them longitudinal. This is an example of longitudinal waves. Okay. And the definition of longitudinal wave is that the particles in the medium, okay, in the medium move parallel to the wave motion, parallel to the wave motion. Okay, let me show you this in this animation here. As you can see here, the particles, this is a tube, and we have air molecules here, okay? And this is the disturbance, the source of the disturbance, which is this diaphragm, as you can see. It's oscillating with a certain frequency, and you can see the wave is moving from left to right. You can see it clearly. And the particle, you can see they are oscillating back and forth. The particles are oscillating back and forth, okay? If you look at this, I don't know if you see this red particle here, it's oscillating. The red particle here, there's a red particle here, it's oscillating back and forth. It's going left and right, okay? It's going left and right, and the wave is going from left to right, okay? So the particles of the medium move parallel to the wave motion. So both of them are moving along the x-axis. So the wave is moving along the x-axis, and the particle is oscillating, making oscillations left and right. Okay, so the two motions are parallel. When the two motions are parallel, we call them longitudinal wave. Remember, when the two motions are perpendicular, we call them transverse waves. Now, some applications of sound waves. Of course, if we didn't have sound waves, we would not be able to hear or to speak, and so on. So if we take this room, for example, and we empty it from air, and I start talking, you will not be able to hear me, and I will not be able to speak, because the medium is not there. There should be a medium where the particle, they have to move. The other application will be looking for oil. People, they use sound waves to look for oil underground. Another application will be sonars, where they use underwater. They send sonar waves, but sound waves, and they are reflected from different objects, and they can navigate submarines, for example. They navigate, or even fish. They use sonar waves to move underwater. Another example will be looking for PHYS, janine, in the body of the mother. So and they use ultrasound. These are sound waves, and they they can take an image of the fetuses. Now let me tell you about the speed of sound. We know that these particles are moving at constant, the wave is moving at constant speed, and the speed of sound, actually, it is depending on the medium, of course. In the air, for example, V at 0 degrees Celsius in the air, okay, the speed of sound at 0 degrees Celsius is 331 meter per second. And the speed of sound in the air at 20 degrees Celsius, it is 343 meter per second. There's a relationship between V at any temperature T and V at 0 degrees Celsius, 331 square of temperature over 273. Of course, this temperature here in Kelvin, you have to be careful, okay? This is in Kelvin. So this relationship between the speed of sound in air at different temperatures. Okay, the speed of sound in water. Okay, in water it is at 20 degrees Celsius 1482 meter per second. We notice that the speed of sound increases as we go to from air to liquid, and V of sound in steel, which is a solid, is 5,941 meter per second. In general, so you notice that the speed of sound increases as we go from air to liquid, from air to liquid to solid. Okay. In general, the speed of sound is given by the bulk modulus divided by the density of the medium. The bulk modulus. This is called the bulk modulus. Okay, and this is the density of the medium. Okay, density. And the bulk modulus in general, B, the bulk modulus, is given by minus P delta V over V. The pressure delta is measured. This is measured. If you apply pressure on your object, there will be a change in volume. So the change in volume over V, the original volume, and the pressure applied will give you the bulk modulus. Okay. That's the formula here. Okay, so if your pressure is positive, you apply a positive pressure, delta V will decrease, and so delta V will be negative. With the negative sign, you get the bulk modulus which is positive. Okay, so this is how you calculate the bulk modulus for, and this you plug it here. That's the density of the medium, and this is V, the speed of sound. Generally, you should know why the speed of sound increases as we go down in these examples here, because you have more. As you go down, the bulk modulus increases. Of course, the density also increases, but the bulk modulus increases more than the density, and therefore this ratio becomes very large as you go from air to water to steel. Also, you should know that the molecules here of the atoms in the steel are very close to each other. Therefore, it's easier for the sound to move through. It's faster for the sound to move through the steel than through the water and through the air. As I told you, if there is a vacuum, the speed of sound will be zero, because we need a medium to have a sound waves, which is longitudinal waves, moving in that medium. Of course, let me show you now here this animation here. This is a tube, and you have air molecules here. These are the air molecules when you have no sound wave moving. Okay, you see the points here, down here. Okay, now here I'm going to send a sound wave, and you can see how the particles are moving and how the wave is moving. This will be clearer than the previous animation. So you can see that the wave is moving to the right. Okay, you can see the wave is moving to the right, and the particle. Let's concentrate on the black particles here. The black particle here is without sound, and the black particle here, the 5 particles here, is the sound wave is moving. Okay, and you can see clearly that the particles are oscillating back and forth while the wave is moving to the right. Okay, you can see here clearly that there are some regions. There are some regions where the particles are very close to each other, and there are some regions where the particles are very far from each other. Okay, this is where the particles are very close, and the distance from here to here is actually the wavelength. That's the wavelength that, and the distance from here to here is also a wavelength. So identical points. Okay, along this x-axis where the wave is moving this is called the wavelength. Okay, of course the particles are oscillating along the x-axis, so you have oscillatory motion. So this is the type of curve you will see as a function of time. This is S. I call S. So the displacement of the particle will be S. Okay, it will not be Y, because the particle is moving along the x-axis. So it will be S of x and t. Okay, S of x and t. Of course, x will be The particle, I'm looking at this particle or this particle or this particle here. So if I change the particle, I'm changing the S here, okay? So this will be equal to Sm, that's the amplitude, maximum displacement, okay? Then cosine Kx minus omega t is a traveling wave, okay? I'm assuming that the phase is 0 here and the wave is moving to the right, okay? I put a minus sign. So this is a sinusoidal wave. This is describing the motion of these points here, the black points which are oscillating back and forth. As you can see, so this is the displacement versus time, and it is represented by that equation there, okay? So this is S, this is displacement of the particle, okay? That's the displacement of the particle, okay? So this is we call this one the displacement amplitude, okay? That's the amplitude that's the maximum displacement. This is, of course, you know this, the wave number that we defined in the previous videos, and this is the angular frequency, frequency of your generator who generates this wave, okay? These waves are generated on the left side and they have a frequency, and this is the angular frequency of that. I can calculate now the transverse velocity of the particle if I want, u of x and t, which is the derivative of this. It will be minus Sm omega, time derivative of course, sine Kx minus omega t, but since we are differentiate cosine, then there will be a plus sign here. A minus sign will come from the omega, and minus sign will come from here. It will be, and we call this here, we call it u max. That's the maximum transverse velocity of the particles. We can also calculate the acceleration if we want of the particle, okay? They accelerate, of course, they have velocities, they have acceleration, and these are called the transverse velocity. Be careful, this is the speed of the wave, and this is the speed of the particles. So you have to be very careful. There's a big difference between the two things. I'm going to differentiate this now. I'm going to take omega outside, so I will have a minus Sm omega squared cosine Kx minus omega t. That's the acceleration of the particles, okay? And we discussed this in details in the previous videos when we were talking about longitudinal transverse waves, waves on a string. Another way to describe sound waves is through the pressure variation. This is displacement wave. We call this displacement wave. Let me show you now in this video here what do I mean by pressure variation. As you can see, by just looking here, you can see that this is the normal situation where there is no wave. No sound wave moving in the medium. You see the particles are equally spaced. That's the air particle, the air molecules, okay? And then you can see when the wave moved, you can see that some places they become a particle far away where you have a pressure has decreased, and some places where the particles are very close to each other where the pressure is high. And you notice one thing very important. As you see here, look at this point here. I'm moving this point at this location, exactly at this time. 1 second, let's say. At this time, I'm looking at the black. Molecules here. Okay, the air molecules. The displacement is 0. You can see it. Displacement is 0 because it is the same as the original. Displacement is 0, but the pressure is very high. You can see it. So the pressure variation is very high, not the pressure. The pressure variation from where? From the normal state. This is the normal situation, and this is the new situation when the wave is moving. You can see here that the pressure variation is very high because the particles are very close, and you can see here I have a maximum pressure variation. Okay? Now if I move to this point here, for example, at this time, you can see, when I go to this time here, you can see the particle has a maximum displacement. I'm looking at the black. Concentrate with me on the black particles. You have a maximum displacement, but the pressure here is what? Is low. The pressure is, there is no change in the pressure, okay? It's very close. You see here, the distance here is exactly as the distance here. So there's no pressure variation. It's normal pressure, but displacement is very high. So what do you notice here? You notice that when the displacement is maximum, the pressure variation is minimum, 0. And when the pressure variation is maximum, displacement is 0. If I have the equation now for the displacement, what will be the equation for the pressure variation? Delta, I'm going to call it delta P of x and t. I'm sure you should know from the math, if you have a function like this, a cosine or a sine, and there's a shift, there's a shift between the two. You can see there's a shift between the two waves, and that shift is exactly pi over 2, okay? The shift is pi over 2, because one is maximum, the other one is 0. So it has to be a shift of pi over 2. So I'm going to write now, I'm going to call this delta PM. That's the pressure, maximum pressure variation, like SM here. Displacement amplitude, there will be the maximum pressure variation. Then the cosine, if you add the pi over 2 here, it becomes the sine, okay? So there will be a sine kx minus omega t. That's the equation for the pressure variation. Variation from where? From the normal state. So this delta P can be positive and can be negative. At this point, delta P is positive. At this time, delta P is negative. At this time, delta P is 0. So you have to be very careful here. So this one here is called, this is called displacement. It's called the pressure. It's called the pressure variation wave. Okay, it's a wave. Okay, it is a wave. You can see it. It's waving. It's a sinusoidal wave, and this is the pressure variation wave. Okay, then this is the maximum pressure variation, okay? And I can show you the pressure variation. I can show you there on the simulation where is this value here. And this is, of course, the wave number, and this is the angular frequency, the same. You'll notice that the argument here, the phase, are exactly the same, but this one is a cosine and this one is a sine, and the shift between the two is pi over 2, okay? The shift, it means one is maximum, the other one is 0, and one is 0, the other one is maximum, and so on. Delta PM, of course, is this value here, which is 1, as you can see it here. Delta P is 0, it means we are in this situation here, okay? When delta P is negative, it means we are in this situation here. That's the situation when delta P is negative. This is a situation where delta P is positive, maximum, okay? You can see it here. This is regarding the displacement wave and the pressure variation wave. These two equations are very important, actually. Okay, this is the displacement wave is here. Okay, and the pressure variation wave is here. Okay, I can. There is in the textbook. There is a formula where it is derived, which shows you the relationship between SM and delta PM. I don't think we are going to derive it here in front of you here. I'm just going to give it to you and discuss it. For the proof, you can go to and look at the textbook. The proof is in detailed there, okay? So let me show you the relationship between the pressure variation and the pressure, the maximum pressure variation, delta PM, and SM, the displacement amplitude, okay? The relationship is as like this, okay? It says delta PM is rho V omega SM. That's the relationship between the pressure variation amplitude and the displacement amplitude. Rho is the density of the medium, V is the speed of the wave, sound waves, and omega is the angular frequency of your source, which is producing these waves. Okay, this is the equation which relates these two quantities. Okay, this one and this one. Okay, remember that k is the same, omega is the same in both equations. So you can, once you get one equation, you can go get the other one by the same omega and k, and by using that formula there. So this is the pressure variation. This is in Pascal units. This is in kilogram per meter cube. Okay, that's the density. This is meter per second. It's a speed. This is radian per second, angular frequency, and this is meter. Okay. All right. Of course, radian is not a unit, so you can put 1/2 here. Then you can notice that the product of these quantities, all of them here, will give you exactly Pascal, which is the units for pressure. Okay. Okay, let me talk to you about what we call the audible range. The audible range, which is the range of frequency where a human ear can detect the sounds. The audible range is given by a frequency between 20 hertz and 20 kilohertz. Okay, kilo means 1,000. Below 20 hertz is called infrasonic region, and this is called the ultrasonic region. So this is the audible range between 20 and 20,000 hertz. The best frequency for a human ear to detect sound is 1,000 hertz. Okay, so the best frequency for human ear to detect the sound is 1,000 hertz. So if we are doing in the air where V is 343, and the density of the air is 1.2 kilogram per meter cube, and we use 1,000 hertz, I can tell you how much are delta PM and how much is SM. For a delta PM for a value of delta PM of 30 Pascal. Now remember, very important number here. This 30 Pascal is, what is the pressure in the room? The pressure in the room is around 10 to the power 5 Pascal. That's 1 atmosphere. And this is only 30 Pascal. It means the pressure variation is very small. For this variation, pressure variation, you put it here, SM for this case, SM, if this is given to you, the SM value is around 10 micrometer. 10 micrometer. Now imagine this distance. These are the oscillation of the particle. This is the maximum distance reached by the particle. The particle is here, and this is the equilibrium, and it's oscillating. This is SM, and this is minus SM. And the particle is, the equilibrium of that particle is here, okay? Now imagine that this distance here is 10 micrometer. It's very small, okay? For this pressure variation. That's the, we call this is the loudest sound. This is the loudest sound. This is the loudest sound for a human ear, okay? And the faintest sound for a human ear, delta, for that one, delta PM is, the value of delta PM is about 30 micropascal. 30 delta PM is 30 micropascal. Micro 10 to the power minus 6, okay? For this case, my SM, if we go to this equation here and put the density of the air, speed of sound in the air, omega is 2 pi f, this is the frequency, and you get SM, you get 10 to the power minus 10 picometer. 10, you get delta SM equal 10 picometer. Of course, pico is 10 to the power minus 12. You imagine how much is the displacement of this particle. It's you cannot see this displacement. That's 10 picometer. Okay, this distance here is 10 picometer for the faintest sound. Okay, that's the loudest sound, and this is the faintest sound. That's delta PM, and that's the SM for these cases. Thank you very much.